and probably, who knows? Who knows what will happen? The world may. All right. Apparently, the more I wear this, the more it sits on my nose. All right, that's a good sign. So welcome to everyone who's here in person. I'm going to have to do this now and do my Chuck Schumer imitation here. If those who are not familiar with Chuck Schumer. Anyway. So welcome in person. I'm used to wandering around, so I apologize for, well, I guess we're not recording the camera, so people on Discord, you'll just have to watch the lecture notes and hear me talk. And it's really weird. These are semi-noise canceling headphones as well. So totally crazy experience. See if I can keep this up for an hour and a half. So hopefully you recognize me as the same person who was on Monday, but now for the rest of the class, we are going to be in person the rest of the semester, or the Arch. One announcement, there is going to be 1 week in late June or mid to late June where we're going to go remote because I had arranged some travel over in Massachusetts that I have to take care of, and I'll probably be either lecturing from there, or we'll be online, or we'll have material ready for that, and we won't have to worry about actually being in class. So there'll be that one week. Let's not forget about that. Other announcements. I noticed that LMS did send out an automatic notification today about the homework 1, and I know at least one person has already done homework 1. I threw that out as a bonus, that you can get a 1-point bonus if you had done it by today, just as an incentive. It's no big deal. This is the easiest homework, hopefully. Certainly trivial if you've already watched the lecture, if you've watched the history of game graphics. Basically everything's in there. I think there's one question, sort of a trick question. Every so often I like to throw in sort of trick questions when there's like subtle details. But other than that, it should be pretty straightforward. And it was also an experiment for me just to see how well LMS and its automatic, what are the parameters and boundaries I have with regards to LMS auto grading, so that we can kind of, everyone will know exactly where they are as much as possible in this course. Because obviously we do a lot of stuff that's project-based, and that can be tricky with regards to knowing exactly, have you done everything, and then suddenly you hand in a project and you find out, yeah, I got it, or I didn't get it, or something like that. So I wanted to have some more things that were sort of immediate feedback, and hopefully the homeworks will be like that. I don't expect them to be very math heavy, or like maybe occasionally you might have to do a little, what is the matrix multiplication? Which one of these matrices is the result of this transformation? That sort of thing, that may show up. But this first one is pretty simple. It is, you should have all gotten a link, or there is a link to in the Discord channel. Keep up with following the Discord, just in case if I need to like post something or answer questions. Basically, I view Discord as being sort of the office hours throughout what we're doing. So much more lax in terms of specific hours, and instead we'll just kind of do our best to be continuously monitoring what's going on Discord. So you should have seen a link to a GitHub Classroom invitation there. I saw a couple of responses. GitHub automatically tells me when people join the project, or go ahead and brought it down, for the Sandbox, right? So the Sandbox, there's actually a question on the homework about the Sandbox, a real simple one, but it just gives me a way to know that, yes, you downloaded the Sandbox, you looked inside, you kind of sniffed around, you kind of know how to make sense out of a the directory structure in there, what is C++, where to look for, what's being included and whatnot, and so on. Right, so it's kind of just general kind of things. The Sandbox application, by default, when it just loads its kind of simple OpenGL thing, draw a triangle, is going to be hopefully deceptively simple in terms of what it does. But there's actually a lot packed in there, especially as we get into using the actual main.cpp portion. It has all sorts of ways to live compile or live use shaders and switch them out on the fly, which is going to be hopefully really useful in this class. And it's also going to provide a means for us to visualize non-OpenGL stuff, because we are going to get into things that are kind of traditional pixel by pixel graphics as well. We're not only going to be, this course isn't only about OpenGL. We're going to focus a lot on OpenGL because that is kind of the fundamental level where so much of the game 3D environment that we live in takes off from. But we don't want to miss out on great things like circle drawing algorithms and Bresenham's line algorithms and fill potentially and drawing a parametric curve pixel by pixel. So that's going to be important for that as well. The sandbox is going to be where we wind up doing a lot of that stuff in. So there's going to be some screen grabs and some questions and back and forth about that. It'll be evolving as we go on. So background on that. We'll look at that a little bit later as well once we get past sort of some of the historical bits and pieces. And let's see, I do want to try, let's see if I can do a presenter mode of this? This is going to be tricky here. I've got to do a Windows. Yeah, let's do this. I don't want to mirror my displays, which may mean we're gonna have to switch a little bit of stuff over on Discord as well. So let's see. Let me just do a quick one here. That display. I remember how to set mirroring. Turn off mirroring. No, not duplicate. Extend. All right, that's good. And I'm going to put this one hopefully up there, and tell OBS Studio to do that. All right, that's not terrible so far. So now get the hang of it here. Almost. So, in the ideal world, we would just talk about abstract graphics algorithms like ray tracing, voxels, how to draw pixels, how to, look at light in an abstract way. If this was a pure computer graphics course, we wouldn't worry about nuts and bolts and like how things actually have to work, how we have to actually deploy things. But we have real practical concerns when it comes to gaming or to producing games. And a lot of what we're going to do is often, how is it convincing enough? How is the lighting good enough? How is the results effective enough? Or perhaps they're going to be graphics that are done entirely for effect, or for, they're stylized, or, maybe it's not even a representation of the real world at all. Maybe it's some sort of on-screen thing, sprites, or, that sort of thing. So we're not going to be talking about strictly kind of pure graphical, kind of theoretical graphic techniques like a lot of other courses might. So we have these practical concerns. That's right. However, of course, like I mentioned before, we will have the opportunity to experiment with pixel level graphics and kind of core fundamental things. But one of the things I like to kind of front load here in the course, and most strictly, because it's going to feel a little bit like, almost like an OpenGL course up front especially, because we want to get graphics on the screen. We want to see the results right away. Even if we want to draw pixel by pixel and kind of draw a line from here to there, well, how do we get it on the screen in a way that makes sense? So why don't we kind of figure out if we can put our cart before the horse, or kill two birds with one stone, or figure out, can we have a chicken and egg at the same time, that sort of thing, right? So we're going to try to do that by introducing OpenGL right away and trying to get ourselves up and running in OpenGL right away, right? In the old days before OpenGL, we would be doing things more like, the pre-GPU. And everybody knows when I say GPU, I mean graphics processing unit, right? We're all familiar with that now. Not so long ago, that was more of a weird thing. I remember back in, I'd say 2008 or so, there was this video, I just watched it not that long ago, of Mythbusters, where they tried to convince people what the difference between a CPU and a GPU was. Has anyone seen that video? It's, you can look for Mythbusters GPU, you'll find it. think I had a link to it. And let's stress myself out here as much as possible. Let's see if I open up another link here. I get to see all of the weird things that I watch on YouTube, if I can get to YouTube. Well, maybe I shouldn't try my luck, or maybe I will. Mythbusters. So this is, one of these is the really, really quick version of it.
I introduced you to Leonardo, and he's going to paint a picture for you guys.
So back a while ago, we needed to explain this sort of thing. The key difference here.
One after the other. And 3, 2, 1.
Right? This is drawing with the CPU. 1 pixel at a time. We have a frame buffer. We write things out. Eventually, we get an image. Right? And in typical Mythbusters style, over the top.
When we hit this trigger on this thing, 2,100 gallons of air.
So this massively parallel idea that with a GPU, there's lots and lots and lots of shaders, of little processors that can individually take care of things like pixel drawing or vertex shading or geometry shading, those sorts of things. So let's
9, 8, 7, 6, 5.
wait for the payoff here.
3, 2, 1.
It's all right. Simple idea. Supposedly simple idea. You'd be surprised how many people, like, there's lots and lots of feedback on this video, like, oh, back, you know, that's not how it all worked. It's, you know, it's, well, CPUs are better anyway. And, you know, people would argue about these sorts of things. Now, with the lens of time, we say, of course, that's, you know, GPUs have won. This was the right way to do it. But the idea behind GPUs versus CPUs is that we can potentially do lots and lots and lots of things in parallel as opposed to interacting with a frame buffer 1 pixel at a time, right? So the old days, pre-pipeline, we would do things like this, right? Early hardware sometimes did have those display processing units, like we mentioned back in the early days, but largely those were just, you know, another CPU that would handle the frame buffer and so on. So the computer that was doing all the simulation and the fun stuff didn't have to worry about the graphics, and the other CPU did, right? So it wasn't that far removed from just another CPU that had a frame buffer that needed to do its thing. So back in the dawn of time, as we mentioned also last time, there was FIGS, right? That programmer's hierarchical image graphic system or something like that. I forget the acronym for FIGS at this point, but it was the early days, you know, was there some sort of graphics language that could be used as some kind of standard way to describe things, to provide, you know, draw models and to interact with a pen or light pen, that sort of things. That was back in the dawn. That was just the beginning, right? We're going to jump over a lot of that, and we're going to go over to modern times. This is a great picture from the movie Modern Times. Those not familiar, Charlie Chaplin, one of the kind of early movies. You should check it out sometime. It's a really great film. It's really short, silent, so on. But it's about, you know, someone dealing with modern times and technology, the advent of technology, and what it, you know, kind of took over work in lots and lots of ways. So we're going to deal mostly with OpenGL, the rise and fall of OpenGL, because arguably right now, OpenGL is sort of in its twilight, sort of, not yet. There's new things that are coming out, but OpenGL is still kind of, you have to learn OpenGL before you get to that new crazy stuff, and it's a great on-ramp to lots of that other stuff. So this is a quote by Jonathan Blow. Anyone familiar with Jonathan Blow? If you're familiar with the game Braid, great indie kind of time, you should check out Braid. It's a great game. It was a incredibly successful independent indie kind of side-scrolling game. Its claim to fame was largely that it did this kind of time reversal gimmick, right? You could play the game and suddenly you could go backwards and interact with certain parts of the game by going back, winding back. Certain things would wind up winding back, other things wouldn't, and back and forth. And he had to come up with this really, really intense system for recording all the gameplay as things changed and go back and forth. So he's pretty well regarded. Anyway, 3D graphics drivers are literally the worst thing ever, right? And that's, I don't know if I entirely, I mean, that's definitely a bit of over the top. But they can be. There'll be times when you're convinced they are, especially if you've got to choose between lots of different ones and make sure what's current on your machine and what you have to deal with. And now even we have to deal with OpenGL. Potentially, maybe we have to deal with Metal or Vulkan or drivers from different manufacturers. Do they support all of the features? With the latest ATI or the latest AMD or the latest NVIDIA or Intel or all these sorts of things that just want to seem to get in the way of what you want to do, right? They're just like all the sorts of things that they didn't quite get it right. Why isn't everybody doing the right thing? Why isn't there just one simple way of doing it? Why do we have to deal with drivers? Why do we have to worry about these things? And that's kind of because of the way that things have developed over the course of time. It wasn't just like OpenGL or graphics, just one person kind of sat down. It's nice to, Ivan Sutherland, a lot of graphics people say, oh yeah, look at that, and say he's where it started, and it wasn't quite that simple. So in a real world, we have to deal with all these kind of things that are kind of growing up out of lots of different places and dealing with lots of different potential standards and lots of different support and things. So I want to talk a little bit about the history. We're going to go into the history of OpenGL and how it got to be where it is. Maybe that'll help you think about where it's going in the future, and even some considerations about when we talk about OpenGL, certain technical issues, where are they coming from potentially? Because even now, we have OpenGL, we have embedded OpenGL or OpenGL ES, we have WebGL, which are all sort of these other branches of OpenGL. And even Vulkan is now the new, or going to be the successor to OpenGL, I guess. So silicon graphics, commonly referred to as SGI, maybe you've heard them under that acronym, but maybe not. Maybe now they're becoming more and more fading in history now. They were a company founded in 1981 that specialized in 3D computer graphics. All the great movies, where, oh, do you have a SGI Octane or an SGI Reality Engine or an SGI 03 and 02 and all that. I had an 03 sitting on my desk at one point. It was really cool. It was this weird kind of purplish, very designed, over-designed case and sort of thing. And so SGI was a 3D computer graphics company specializing in that. They developed software and hardware specifically for this purpose, right? One software that they developed was called IRIS-GL, which stood for the Integrated Raster Imaging System Graphics Library, IRIS-GL. It was used to generate 2D and 3D graphics on SGI's high-performance machines, and despite it being very popular at the time in all the Hollywood movies, everybody, it was the big thing, it had one major problem, and that was it was proprietary, right? It suffered from the thing that I just said, boy, wouldn't it have been nice if everyone had just developed from a common thing, right? If everyone just came up from that one thing and everybody shared in that, that'd be great. And the problem for SGI was that was precisely the problem. They developed the hardware, they developed the software, they were the only ones who had it. It was all exciting and so on, but all the burden was on them. Right? It's a very closed proprietary system for doing this. So it relied on everything. And of course, the popularity of movies and graphics and so on, everyone saw that as a great thing to potentially happen. And other companies wanted to do different things. And there was pushes from the people who were using SGI products. Well, could we use this on that, or could somebody else develop hardware that used your software? Could we run your whatever on, so on and so on? And out of that sort of thing, that realization that as desktop computers got faster, different things, cheaper, more inexpensive, more efficient. Eventually, this bold move happened. SGI cleaned up IRIS-GL. They removed all the functionality that did not relate to computer graphics, and they released it to the public in 1992, which sounds like, to me, just like yesterday, but to you, it's a lifetime ago. Kind of crazy, right? How many, is it 30 years yet? Almost 30 years? That close to 30 years ago? Released to the public in 1992 as OpenGL. So OpenGL is coming up on a 30th birthday next year, I guess. Wow. And that was the first, in terms of being a real cross-platform standardized API for real-time computer graphics. So from the get-go, they were like, okay, trying to build in optimizations that would lead to real-time performance. SGI did not provide any actual source code for it, which is interesting. It was merely a specification of how the API should work. Right, so this is a functional specification. They just said, okay, here's what you need to do, here's what the API should be, here's what the functions should be. But they didn't tell you, okay, how do you actually have to do that? How do you actually have to draw a line? That's up to you. But you're going to have to know how to draw a line. You're going to have to know how to set up certain geometries and so on. Right? That's kind of a bold move. So the cool thing about that, and the not so cool thing about that, was that OpenGL wound up being supported across many platforms and devices. Right? Modern days, everything to some degree, even the Mac still kind of supports it a little bit, sort of, kind of. Right? So it's very, very widespread. Right? People could implement their own stuff to that standard. Right? They didn't have to worry about, okay, can I get this code running on my machine? They just said, okay, what parts of this do I need to kind of present to the public as an API to make it work? So that worked pretty well. Lots of devices supported OpenGL. But the greatest advantage was that support for potential extensions and customizations. And if you wanted to build new hardware that did a certain thing, you could do it in certain ways. So it allowed the manufacturers, allowed the hardware companies to kind of extend it as they wanted to, which was very appealing to those sorts. All right. However, in typical style, along comes Microsoft, and Microsoft has this history, of course, of saying, well, we have, some, even before Apple had I guess Apple had the reputation, right? But to some degree, Microsoft is always saying, well, how can we come up with a better way of doing it, or, jumping on some bandwagon of doing it? But OpenGL was supported and implemented on Unix-based workstations. SGI workstations were largely kind of flavors of Unix. And when Microsoft entered the market with their workstation, it was based on Windows NT, or New Technology. That's the rumor that it actually stood for that. We'll talk about Windows NT trivia anyway. That was in 1993. So Windows NT was released as a direct competitor to Unix with networking and so on, and 32-bit hardware support, but it had no 3D graphics library native to the system. Microsoft pledged that they would support OpenGL. So that was all fine and good. And NT 3.5 was the first version of Windows to support OpenGL, and it barely did. So they finally got around to implementing OpenGL in 3.5. It was released in 1994, but only as a sample implementation. So they kind of were able to say, yeah, we checked the box. This is great. This is what Microsoft has often done, right? They get something compatible going, and they say, okay, we'll offer this. It's great. It's going to be a platform. But there wasn't a lot going on. There wasn't dedicated cards, right? There weren't things that were really capable of running it. PCs were not, there were CGA, EGA, frame buffer kind of graphics on there. There was no graphic accelerators and so on. However, Microsoft knew that people wanted to play games on their computers, because there were lots of computers on people's desktops out there. And certainly in the late 80s, early 90s, PCs were taking off, and that was of interest. So it was a big opportunity for Microsoft, and they decided that rather than really push on OpenGL and open standards, that they would decide to introduce their own technology called DirectX. And DirectX wasn't set up to be necessarily Direct 3D. It was a whole umbrella of things. There's direct sound, and there was direct movie, direct show, a bunch of direct kind of technologies at the time. But the big one that most people now probably know it for DirectX is the 3D acceleration and so on. But before DirectX and Direct3D was a thing, their first attempt was something called WinG, so graphics for Windows, which simply passed commands to the underlying graphics device interface and offered no real 3D functionality of its own. But eventually, Microsoft acquired a company named, let's see, I have to get my own notes here, acquired a company called RenderMorphics in 1995, who produced a 3D graphics API called Reality Lab, which was then renamed and shipped as Direct3D. It was part of an SDK that included, like I mentioned, Direct Draw, Direct Input, Direct Play, and Direct Sound. So Direct Play provided an interface to, kind of controllers and things, Direct Sound to the sound cards and so on, all these things. The first versions of Direct3D were uncomfortable to work with, and developers were slow to adopt it, which caused Microsoft to keep supporting OpenGL because developers liked it. So despite Microsoft's initial efforts, they supported OpenGL. Where am I? So OpenGL 1.1 was implemented in Windows 95, but there was, trouble brewing. These are the API wars. So Microsoft tried to push this notion that, well, we're going to support OpenGL because OpenGL is the professional thing. They tried to kind of say, well, OpenGL, we're going to do what's necessary for that because we wanted to see, people use it for Maya and Softimage, 3D Studio Max, kind of high-end things. But for games, for desktop graphics, they said, well, we want to develop our own thing. We want to own the desktop. So Microsoft has always tried to be out there owning the desktop. And sure enough, that's been their stance, right? Eventually, despite a lot of game companies and developers like John Carmack, like id and Doom, and the folks behind Quake and so on, GL Quake eventually came out. They were like, no, we can use this thing. GL is great. We can use it in our games. Microsoft's like, no, let's stay away from there. So there were wars sort of brewing. Now, eventually, there's a quote. I think this is a John Carmack quote. Yes. So you can read this. Direct3D immediate mode, immediate mode. That's something that's going to come back, and we're going to talk about that in kind of various things. It's a horribly broken API. It inflicts great pain and suffering on programmers using it without returning any significant advantages. I don't think that there's any market segment that Direct3D is appropriate for. OpenGL seems to work just fine for everything from Quake to Softimage. There is no good technical reasons for the existence of Direct3D. So that was John Carmack, a very vocal, back then there were rock stars of game graphics. John Carmack, John Romero, American McGee, some other folks who are escaping. Well, of course, our own Curtis Priam kind of folks out there. Now, what happened here? So this is the John Carmack quote. Yeah, there he is. Met him once. Very nice guy. Very nice guy. Despite him sounding like, really kind of, when he doesn't believe in a technology, he's very frank about it. But a very nice guy. So despite that, Microsoft continued. And in the interest of time, let's see, how deep do I want to go into here? I don't think this one adds all that much. It's basically the back and forth of kind of what was going on in the warring states between OpenGL and Direct3D. And it's with us today. It's still there. Still there. So this never ended, right? Back and forth, Microsoft's doing their thing. And in those early days, There was also hardware wars sort of in their early days. And the first two to the table, or the big names that we still recognize to the table, 3DFX for historical reasons. They created what was considered the first sort of 3D accelerator that was kind of a dedicated card that was, it wasn't a graphics card, it was a 3D accelerator card. Right, so Priam and NVIDIA and folks, they get credit more for just a straight 3D or a straight PC graphics cards. But 3DFX came along and said, yeah, we need, there's a certain segment of the market, PC gamers, who would be willing to pay extra for 3D performance. And they created their Voodoo graphics cards. And this is a big to-do back in the day. All right, this is more in the late 90s. And we had the first glimpses of what would then become, kind of the common GPUs that we work with today. All right. Eventually, ATI. There was Creative Labs. There was 3D Labs. The list goes on and on and on. It used to be lots and lots of graphics cards companies. Matrox did lots of graphics. I think Matrox is still around doing some cards and things. But these days, largely, we've kind of come to ATI and NVIDIA, or AMD and NVIDIA. But DirectX has evolved. It's kind of come along, and it's doing its thing. And there's it has been interesting in that now, or at least through this moment of time, there's lots of back and forth. So it's like everyone's trying to leapfrog each other, hopscotch, whatever. And they would adopt one another's features back and forth. And things started to happen in DirectX 8 was one of the big milestones as far as DirectX goes, where we started getting into shading and GPUs doing kind of more what we're thinking about today. This is in the 2000s or so, early 2000s. Shaders really started to take hold. Now, how many of you, when I talk about shaders, know what I mean? Right? A little bit? Okay, shaders is going to be a very, very big theme. And we're going to get into that in a minute as we get into, past the history. What are these things? What are they really doing? But this is when they kind of happen. So 20 years ago, shaders started. That's the important part. And nowadays, we're up to DirectX 12, and that's OpenGL has kind of stopped trying to compete with DirectX, and now it's the way we have Vulkan sort of coming. And I have a note for myself to mention trivia here. So obviously DirectX has been on all the Microsoft platforms. It's been for Windows. The problem is, its proprietary nature. It's been on Xbox, so Microsoft has sort of tried to do this thing where, okay, it's easy to develop on PCs and for the Xbox. Clever move on their part. There is one non-Microsoft platform that DirectX was on. That is an interesting, that not many people realize, which I guess didn't get a lot of use, but some people spent a lot of time on. Can anyone guess what platform, what console that was a non-Microsoft console that DirectX appeared on? It happened before, let's say before the Xbox came to the scene. So there's a hint. Sorry? It was not a Nintendo, no. It was actually the Sega Dreamcast. So right before Sega stopped making hardware, and I personally, I think, I don't know, it's kind of coincidence that right after the Dreamcast, kind of couldn't get its feet, Xbox happened. Who knows? But interesting times. Those were certainly interesting times. The company I worked with, we worked with some very early versions of DirectX and DirectShow and Direct Movie and so on, because we were doing, well, we always did, video compression and FMV and so on. So in addition to supporting all the proprietary open pieces, we were always motivated to be as compatible with whatever plugins and systems there were. So we were asked by Sega to make sure that all of our tools worked on DirectX for the Sega Dreamcast. It was a very interesting, convoluted beast that, of all the games, I think I did one game that actually deployed with that. So one of the problems that OpenGL had was, of course, SGI was this company that it was attached to, and it continues to sort of be attached to. SGI wasn't really, had no particular real kind of motivation, and a lot of different other companies wanted to get involved, and so on and so forth. So eventually, in an effort to kind of get themselves going again, win back some of the momentum from Direct3D, DirectX, the different people who supported it and SGI, they decided at one point they were going to figure out, okay, we've got to get our act together. We've got to support more of these features. We have to all agree on things. So around 2004, 2006, somewhat in that time frame, when Direct3D was kind of dominating what was going on, and when the Xbox 360 came out, OpenGL was on shaky ground. So OpenGL kind of came out with or made all sorts of promises. SGI switched OpenGL over to this new Kronos group, which was representatives from all sorts of different companies, including SGI and NVIDIA and everybody at Microsoft, I think. Maybe they had the SPY in there, who knows? Microsoft would do that too, it wasn't beneath them. So Kronos group was created to kind of hopefully kickstart and preserve and keep OpenGL going, which it did. It was a little bit shaky. There were lots of promised features. There was lots of things that were, okay, it looks like there's going to be a clear path for OpenGL to catch up with everything that's going on in DirectX and so on. And that didn't really quite happen. They kind of overpromised and underdelivered, eventually kind of forced themselves to kind of deliver certain things. And sort of the last big good releases or interesting releases were like OpenGL 3, 3.1, 3.2, 3.3, and then eventually 4.0. And they eventually came to realize that, well, okay, maybe just OpenGL itself is sort of long in the tooth, right? We had all these different versions. We had different versions of the shading language versus the OpenGL core, and so on and so forth. And the good versions are all basically right around here, right? 3.3. Most of what we do in this class, a good chunk of it, lives here in the 3.3 part. Some of it in the 4.0, but mostly in the 3.3. Those good versions also typically live on OpenGL ES for embedded systems or your kind of portable devices. So there is reasonable support for it. You can do all kinds of good stuff in it. I mean, you probably play a lot of games without realizing it, experience a lot of things that are using OpenGL 3.3 and 4.0. It's very capable. I don't mean to make it sound like bad. It's pretty amazing what you can do, even in terms of the latest physically based rendering and all that kind of stuff. We can do some amazing things. It's not until you get sort of like really advanced that we start to run into things that you can't do. But we also have a really fun piece called WebGL, which is based on OpenGL. So if you know OpenGL and you want to do 3D graphics for the web, really good contender, right? That's based more around JavaScript, but a lot of the APIs are going to be similar to the 3.3 OpenGL, right? So you get a lot of bang for the buck by learning OpenGL, even though sort of we have this looming future, this Vulkan. And we'll talk about Vulkan a bit. There are some Vulkan tutorials. Once we get past all the basic stuff and we're ready for it, we'll get a little bit into Vulkan. If you want to feel really motivated and excited, there's potentially ways to maybe do some Vulkan stuff as part of your final project. Okay, so that's the basics of the history of OpenGL. Way back in the day, SGI, battles with Microsoft, gaming world was like, we don't want to be beholden to Microsoft, et cetera, right? So now that we know its roots from a historical point of view, what about the technical basic building blocks, right? We can talk about pixels. That seems to be a fairly obvious thing to do, right? Pixels, after all, when we think of graphics, we think of pixels. So are the basic building blocks of OpenGL pixels? And no, they're not, right? So we're really not going to talk about pixels all that much in regard to OpenGL. We're going to talk maybe potentially about texels and things, and we're going to use pixels to generate texels and all that stuff eventually. But what we're really going to concern ourselves with is polygons, right? You've all heard of polygons, low poly art, complex poly, mostly triangles now specifically, right? Polygons or triangles is a great optimal choice as far as polygons go for lots and lots of different reasons. And they form sort of the basic building block of how we're going to develop things in OpenGL. And the nice thing is, using them, we can really kind of represent anything, right? So even if you're talking about eventually doing voxel graphics or NURBS, non-uniform rational B-splines, or parametric surfaces and all that, there's lots and lots of ways to start off with just, okay, draw a line, draw a teeny, tiny, tiny little line, or draw a cube that is just your unit, your voxel, and build up from there, right? So we can jump off from there and get there. But polygons are a great building block. And for right now, game graphics, desktop graphics, that's largely what we're going to use, right? Even when you see the latest engine from wherever, it does this amazing new graphic stuff, you got to think, well, what hardware are they running on? They're running it on hardware that's doing stuff in terms of polygons and fill and shading and so on and so on. Right. So it's a good choice. We use it for now, right? And specifically, we'll talk about triangles, right? Historical footnote, that 5th generation of consumer devices that we talked about. If you, I was going to ask, what are the differences in the 5th generation of home consoles? We had the Sega Saturn, we had the Nintendo 64, and we had the PS1, or just the PlayStation at the time. Unfortunately, or to make life interesting, Sega chose to support quads instead of triangles, which everyone else did. And quads are not great to work with, right? You might think, hey, 4 sides, flat surfaces, tabletops. That's 4 things, but they're actually not ideal to work with, right? So we're going to deal with triangles, and we're going to talk about things like triangulation. So we're going to break down complex things into triangles, meshes, surfaces made of triangles, right? There's a term called tessellation. That's when we break down a surface into other smaller parts that we can represent it with. So we have tessellation. Surfaces and meshes are tessellated into triangles. Triangles are ideal to work with in a lot of regards. We'll talk about more in a second. Almost all modern graphics hardware is designed for triangle rasterization, right? You feed them triangles in, they're going to draw them, color them, fill them in, get them on the screen somehow, right? There are still cons. There are, this tessellation and triangulation isn't necessarily ideal. Tessellation is normally a fixed process. This is changing a lot now. I don't know how many of you, if you're really enthusiastic about computer graphics and games and so on, you may have seen Epic just did a, what was it, the big reveal on UE Engine 5. They can have an advanced access, early access version of it. They're talking about ways that you can take complex meshes and it'll automatically do all kinds of great stuff in terms of subdividing and making them smaller and more efficient, more compact, and so on. So this part is kind of changing really fast, but tessellation in its simple form is the idea we can take some kind of surface, or we want to build some surface and make it out of sort of a generally a regular distribution of triangles, right? Imagine if you're taking a circle or a sphere or a cube, there's going to be some ways to kind of simply break that down, right? A flat surface, okay, we have a square. Here's where I say, do we have any? Yes, we do. I promised myself I'd actually write on a whiteboard. I'd actually have some real are people online, still online? So I should be able to hear you. If I don't hear anyone. Okay. All right. So you won't see this, but what I want you to do is draw a box if you're not seeing this part, right? We have four corners of a box. We have a quad, and real simple way to tessellate a quad is basically just draw a diagonal. Boom, done. Triangles, right? Imagine you want to create a cylinder. What do? Well, you create a ring of quads that have been tessellated into triangles, right? So now we have a way to have a cylinder. We're going to always approximate other shapes and meshes using some combination of triangles, right? But the simple ways to do them can be kind of fixed, can lead to kind of blocky silhouettes and blocky features, that low poly look. This is sort of like Sutherland's quote, where he said, that Z buffering will never work because you'll never have enough memory to do it. It'll be too expensive. Right now, it's like, oh, you'll never have enough triangles to keep your stuff from looking blocky. Well, that's obviously changing or already changed. Or if you look at fifth generation first occurrence of a lot of game graphics in again back in the Dreamcast, PS1, Nintendo day, we had lots of blocky silhouettes and some clever ways to keep it from looking blocky, but low poly is now more of an aesthetic thing than a limitation for us. All right, so let's consider that lowly triangle, the humble triangle. Let's see, can I make this bigger? Oh, I can do that. All right, that's better. All right, now what I see over here makes a lot more sense. So since the triangle is going to be our basic building block, we have to talk about certain things about it. First off, the representation. Right? We represent a triangle through 3 points, right? No big surprise there, right? It has 3 vertices, right? 3 points, each known as a vertex. We have V1, V2, V3. We have the triangle. If we have those 3 vertices, we know everything we need to know about the triangle, right? Well, not exactly. There are some things that we can kind of assume from that, but we're going to eventually we're going to specify a lot more than 3 points. But let's this is one of the cool things about triangles. Their planar nature. 3 points on a triangle always lie on the same plane. That's why the stools with 3 legs are so great. The great analogy, right? You can always 3-legged stools never teeter, right? They always occupy the same plane, which is a lot better than quad, which can be non-planar. Imagine you could have, a quad. Again, people at home, you're going to have to imagine this a little bit more. I'm going to draw that diagonal across the square, but I haven't filled in. So I have 4 dots, the diagonal across the middle. But imagine, as I'm drawing this, I'm not drawing it on a plane. So I'm going to think about this, the lower right point being out here in front of the piece of paper, the screen, where I'm drawing it out here. It's somewhere right here where the tip of my marker would be. And the other one will also be out there, right? So if this point was really out here, we're going to create this sort of like origami shape where there's a crease in the middle of it, right? So potentially quads can be creased along across any 2 vertices, which can be very bad, right? It's hard to draw that. Suddenly they become inherently kind of non-planar, right? They're a complex surface in and of themselves. Not great. Lend itself to rendering artifacts and all sorts of other things that are going to be problematic. Now, here's one of these cool things that we can assume about triangles, or we're going to use this as an assumption to help us out in a lot of ways, right? We want to think about the triangle not just as the set of points, but also the surface, right? It's an actual polygon. There's something in between all of these things, potentially, right? It's not just a set of lines, it's also that bit of surface in between. So it might have potentially 2 sides to it, a front and a back. So that might be interesting. You might have one side is blue, the other side is red, One side is facing the camera, the other side is not facing the camera. Right? So you got to start thinking of these things as being physical sort of stuff. And one thing we take on as a kind of standard practice is this notion of winding order. So when we talk about the three vertices of a triangle, the order is important, right? Because when you use that order to say, okay, which side faces us versus which side doesn't, right? So it can be either clockwise or counterclockwise. How do we really know that, how does it really tell us that? Well, we'll get to that as we start to get into math, specifically this normal calculation. How many of you are familiar with the cross product, right? You should be familiar with the cross product. It should be a simple cell here, right? The notion that if I cross two vectors, I wind up with a vector that's normal, that's tangent to the plane that those other vectors define, or vectors are on. So we can use that same sort of thing. We can cross certain edges with one another, and that'll give us a normal. It gives us a thing that points in some direction. So it'll tell us if it points towards us, it's at the front. If it points away from us, it's at the back. So depending on the order, right, we'll know is it effectively sort of, the right-hand rule facing in or out of the screen or facing us and so on. Right, so we can use that to figure it out. Any two vertices, their normal is going to be pointing in a similar direction as long as you are maintaining that order there. Right, so just by using a simple cross product, as long as we know what order to do them in, makes sense. Right. So next thing up, we mentioned triangles being really good at representing meshes because you can form any other surface from there. So we're going to deal with collections of triangles or meshes, refer to them in a big way. And so one of the concepts we're going to talk about with triangles is that each of its vertices is potentially unique in the world, but a vertex might be shared among multiple triangles. Right? In our case of our meshes, our tessellated meshes that we created, that dolphin, lots of those, a particular, jump back to the dolphin. Right. If you look at the dot or the vertex at the base of its dorsal fin there, it actually is shared across, let's see, 1, 2, 3, 4, 5, 6, 7 different polygons, 7 different triangles, all share that same vertex. Right. So that's a important sort of thing that we're going to take advantage of. Right? So for each triangle, there are 3 potential vertexes that make up that triangle. However, we can reuse those vertices as we get into working with meshes and more complex objects. Right? And they provide us not just with convenience in that way, but also efficiency. Right? We don't have to have necessarily the same thing repeated 7 times like we would have in the case of that dolphin, and it eliminates the possibility that one of those representations is slightly wrong, which might lead to some kind of misalignment or a hole in our model or things, right? If we're always referring to the exact same vertex, we know that things are meeting at that exact point, so we can make them watertight. They hold gas, so on and so on. But they're also efficient as far as memory usage goes, right? We don't have to specify everything about every vertex every time. We can say, okay, here's the vertex I'm interested in, and maybe I'm going to use it across a whole bunch of different things, right? So in this, in the diagram, the one on the right, it has distinct vertices for each of the triangles because they're not shared. The one on the left, we only have 1, 2, 3, 4, 5, 6, 7 vertices to the whole thing, and each polygon is going to have 3 indices that tell us which vertices it uses. Right? So it might be 0, 1, 2, and this one uses 1, 2, 3, and the next one uses 1, 3, 4, right? Kind of like this. And I got the numbering wrong, sorry. Off the top of my head, I was doing wrong. So The idea is that we store indexed triangle lists. Right? There are other ways to kind of break this, and you can even use quads. You can use points and so on, but the normal way we're doing things, and again, the game adaptation, the game use of these things, we're typically talking about these triangle lists and meshes this way. So if you really look at OpenGL, you say, hey, look, I can draw a point. Yes, you can. I can draw a quad. Yes, you can. But don't. Right. So triangles are specified often by supplying 3 vertex indices. So in this example, we have 6 triangles, and they share those 7 vertices. So that's a triangle list. To get even more efficient, to even be more ambitious, we can also do things with triangle strips, right? Flexible triangles. Now these are most handy in things that have been uniformly tessellated, right? They have kind of these uniform strips that are made up of triangles that don't necessarily have to be rectangular by any means, but they occur in a certain order, and triangles connected to triangles connected to triangle, and so on and so on. Right? It's similar to an index triangle list, but after the first 3 indices, all you need to do to create the next triangle is give you one more index, right? Because it uses the last 2 that it got plus 1, and then the last 2 plus 1, the last 2 plus 1, and so on. Right? So in this example, we give it 0, 1, and 2, and then the next triangle is formed by just saying, okay, here's index 3, and it uses 1 and 2 again. The next triangle, we just give it 4, and we use 2, 3, and 4, and so on, and so on, and so on. Really, really efficient. This is why we love triangles. Right? And essentially, n minus 2, n minus 1, n to create those, but the 2 previous values swap places to maintain winding order, right? So depending on how you want to do things, remember we have that front and back, right? So you might want to be careful as we get into that things, but nothing is quite ever as simple as it seems, and you'll run into these kind of special cases. So triangles are going to be what we work with, right? OpenGL, graphics cards, even Vulkan, all these things love triangles, triangle lists, triangle strips, and so on. So how do we draw triangles? What are the mechanisms? How does OpenGL do it? All right. First, going to talk about this thing called immediate mode, which we'll talk about. You'll see, I think by default, the Sandbox draws its first triangle in immediate mode. But once we see it done and we talk about it, and you experiment with it and you see it, never do it again. It's old. It's a remnant of this sort of fixed, what we call the fixed function pipeline, where typically up at the CPU level we have this geometry specification where we would define a triangle by saying, okay, I'm going to start drawing a triangle now. Here's a vertex. Here's a vertex. Here's a vertex. Done. There's a triangle. And it would, as we were doing that, the moment we had done, it would draw that triangle. Right? So here's another triangle, here's the vertex, and the moment I'm done, it draws that. Right? This is what immediate mode means. The moment I say I'm done specifying a piece of geometry, it would draw it. Right? And this is all part of this, this fixed function pipeline, where the hardware basically was going to do certain things, a lot like the display processing unit of the early days sort of thing. So the CPU would provide the geometry specification, then everything else would be through that API in a certain order, and you would just kind of specify things, and eventually it'd be rasterized, drawn, and so on. So we had the model transformation, camera transformation, lighting, projection transform, clipping, rasterization, texturing, and fragment shading. All right? So a lot of these techniques wind up carrying forward, but in the early days, the hardware and OpenGL kind of abstracted it all away from you. So we won't worry about those other than saying that, yes, they are in there. We're going to talk about more the modern version instead, right? So there were, this is immediate mode, right? Specify individual vertices and attributes with individual API calls that would get ultimately rendered. You had certain calls that were also therefore transformations. right? A transformation being, okay, I have this vertex that's made up of I have this triangle that's made of these 3 vertices. They are points in space somewhere, but maybe I want to move them around according to where the camera sees them. Or maybe they're part of a mesh and I move that mesh around. Right? So there's some kind of transformation that they go through. Or maybe I have a model that I want to scale up big. Right? Scaling, rotation, and translation are our 3 types of transformations that we go through, and we can combine them into single transformations as well. So we tell basically once we have a mesh or we have a triangle, we have some kind of transformation that we're allowed to go through to kind of say how that triangle really shows up in the world or is presented to the camera viewing that world. So we'd have things like, we would load the identity, which would just be a boring, okay, I'm looking at it straight on. And then you might say, okay, translate, you can sort of think of it in primitive ways, saying, okay, move the camera or move the model, one or the other, right? And then maybe you rotate. Do you rotate the camera around the model or you rotate the model itself? Right? Those are the sort of transformations that you go through. You'd set that up. Setting up a triangle would look like this. You would say GL begin, tell it, yeah, I'm drawing triangles, and then give it every vertex along the way. This is that immediate mode. Yikes, right? And you might say, all right, along the way, in between as you're specifying, you can do it, vertex by vertex, or just all at once. You could say, okay, GL color 3, give it an R, a red, a green, and a blue value. So you could specify the color of each vertex. Right? You're not specifying the color of a triangle. You kind of are, but you're actually specifying the color of the vertex. We're always talking about vertices, and their attributes. Right? So a red triangle is actually made up of 3 vertices that are each red. Right? Think of it that way. It's not a red triangle. It is a triangle defined by 3 red vertices. But in this case, in immediate mode, it would just say, well, okay, until you change it, I'm going to assume that's the value for everything until you tell me otherwise. So if I gave it a bunch of vertices at this point, it would assume they were all using that same color. Now, texturing was done similar. We're going to talk more specifically about texturing in a minute. Texturing, in general, okay, introduce the concept. How many are familiar with texturing at all? Right? A little bit, if you've developed a game. The basic idea, and this is back in the day when it was just brute force, up until fairly recently, the notion of providing all of your geometry and all of your detail actually through the model was kind of scary in that, well, how could you possibly reproduce the world in enough detail using the actual geometry? It'd be ridiculously expensive to really specify every point on every surface and exactly how it is. So, as a shortcut, sort of a shortcut, it's useful for a lot of things other than just that as well, is this notion of using a texture, which is a lot like a bitmap or a graphic. We can start off just thinking of them as sort of bitmaps. And you would say, all right, on a triangle, rather than drawing it a certain color or specifying a color for a vertex, or allowing it to calculate what color a pixel on that should be, we would give it a bitmap, and it would draw that bitmap on that triangle. Basically, it would sort of create in the early days, think of it as a decal or a sticker. Right? So the sticker would be, okay, this is a brick wall. What do I want to put the brick wall on? Right? There's some geometry out there. I'm going to make this look like a brick wall. I don't want to say that it's got actual bricks in, but I have this sheet that looks a lot like bricks and plastered on there, lay it down on there. Doesn't matter if it's a beach ball, whatever. I need to maybe cut it into facets and so on so they fit on those. But I can make a beach ball that looks like it's made of brick because I use this texture on there. Right? So there were calls to say, all right, where does that information come from? How do I know, you had this sheet, the sticker sheet that looked like a lot like a brick wall. How do I point from my vertex over here? How does it know where on the sticker sheet to draw from? Right, so that's those coordinates there. So this is all the old day stuff. And the idea, fixed function pipeline, is largely okay. You give it a bunch of values, you say, okay, I'm done, render it, and it would do its thing, right? A, B, and C, and you get back X, Y, and Z. That was immediate mode. Let's never go there again, all right? Because it's fixed function. It only does what you tell it. You don't have the ability to interact pixel by pixel or vertex by vertex and so on. You just kind of have to specify everything all the time and then let it do its thing, and then you update everything and do it over and over again. So instead, we're going to be using modern OpenGL, which is a programmable pipeline. So different parts of that other pipeline, we can now kind of provide code to say, okay, when you specify a vertex, here's how we're going to process that vertex. Or when it comes time to draw this particular fragment on the screen, this pixel on the screen that corresponds to the thing we would see if that triangle happened to be occupying that space, you can take responsibility for how that gets drawn. You could implement different ways that light interacts with it, for example, right? Some particular orientation of the pixel according to where it wound up and so on. Right? So there's lots and lots of different things you can do by programming that. To make that possible, to make that efficient, we now talk about, it used to be called retained mode. Now we just talk mostly about open or about modern OpenGL. We don't really refer to it as retained mode or some sort of scene-based mode or graph-based. And the idea is that you would define something as a set of buffers, give a graphics card, give your renderer those buffers, also give the graphics card a bunch of little programs that say, okay, how to process those. And those little programs are our shaders. Right? And then the CPU just sits there saying, okay, I need to update something. Let me update just the least amount of thing and then tell the GPU to go process all those things because those buffers have already been retained by the graphics hardware, right? You only change what you absolutely need to change, or you give some smaller subset. Okay, here's a new transformation, but here's this complex model made up of a billion pixels or a billion polygons. I don't want to tell you every time every frame is drawn, you need another billion polygons. But it's okay for me to tell you, okay, turn it to the left, rotate it around this point. That's pretty efficient. But the hardware, the graphics, the GPU, the card, you don't want to be passing things back and forth. So we have the modern pipeline for that. All right. There's no more direct drawing by the CPU. The CPU never says, okay, everything I just specified now draw. Right. Instead, we are going to store everything as buffers, and then the graphics hardware is going to determine how to draw those buffers. We are going to kind of kick it off and tell, okay, now it's time to go. The buffers are complete. Do your thing with them. But it's not directly. We're not each frame. We're just more or less saying, okay, draw everything you got over there. You know what to do. Go ahead, draw it again. Draw it again. Right. So we're not directly responsible for polygon by polygon anymore. So, like I said, to implement that, we're going to have to somehow give the graphics card buffers of data, right? So to do that, we have some main functions called, you see these GL gen buffers. When we want to generate something, we have gen functions to do that. We have gen textures, gen buffers, gen that sort of thing. When we want to use something, we want to kind of set the state of what we're modifying. Usually we're talking about something called binding. So if we want to say, okay, I have the state right now and I want to bind this new buffer in there, so tell the state, okay, here's this new buffer I want to use. You're going to have a bind call for that, right? This new set of vertex arrays. I'm going to bind this set of vertex arrays. I have a new buffer, bind that buffer. New texture, you might bind the texture. Right? So binding is sort of like, okay, give it that right now. It's not saying load it. It's not saying push all the data there. It's just saying use that one. There's other calls that actually do that transfer, the buffer data, right? There's some other buffer, partial buffers and things when you want to just update a piece of a buffer, do that as well. But there's another call for that. So these become sort of the main functions you're going to see over and over, where when we want to sort of tell the graphics card, reserve a buffer, use a buffer, copy something into that buffer, we have those functions. And of course we have to tell it, how are those things organized? For that, we have another function, GL vertex attribute pointer. So every vertex is going to have a set of attributes. So far, vertex, interactive part. I'm used to just talking onto the screen now. I can actually ask questions and hope people are answering. Imagine I have a vertex. Give me one attribute of that vertex. Yeah. Position, right? Fundamental thing. The vertex has a position. So sort of at a minimum, we're going to have a buffer that contains the positions of the vertices. Right? So that's step one. As long as we're doing, because ways are really weird things, and I'll show you some of the tricks like that you don't do that are really, really wrong, but they can lend themselves to interesting ways. That's the other cool thing about graphics in games. We look for the ways that we can do cool stuff that's wrong, right? It's not the theoretically right way to do things, but that's what leads to a lot of these things. The tricks that we get, okay, how can we get there? And then suddenly that brute force thing that we came up with that was just like a crazy idea, that winds up being something amazing. So we'll look at how to break some of these things along the way and how to do weird things. The Sandbox does one of these right away. Yes?
So does the buffer act kind of like a RAM for short-term memory?
So I'm not sure I heard all. This is really going to be fun. Between masks, let me interpret it though. So the question is more like, where do those buffers live? Are they in the RAM of the CPU? Are they in the RAM of the GPU? And the answer is yes. They're going to start off. You have to load them somehow. So the CPU, you're always, you start with your programming in the CPU. That's where our programs are going to live. So you're going to have to say, okay, I stream a model off of the disk, or I have some kind of set of vertices in my program that's in an array somewhere, and we'll see that. So your CPU program will have that. And then at some point after it, the CPU asks the GPU, set aside a buffer for me, would you? And then it'll say, okay, now here's the data, and it'll throw that data down there. Right? So then it will live on the GPU. So there's a transfer that occurs there. Right? So there's going to be lots and lots of other different types of vertex attributes. The data that you pass, this is going to get interesting real quick. It can be either separated or interleaved. Does anyone know what I mean when I say interleaved? Okay. So say we have a set of positions, right? Because all our vertices need their positions. And then I come along and I say, okay, now I want to have colors for those as well, or normals, or whatever attributes I want for those vertices. I have two choices, and it's up to you to decide which you like to use. There's different efficiencies, and these days I think it doesn't quite matter as much as it maybe used to once upon a time. But you can say, okay, here's a buffer that contains all of the positions. Here's another buffer that contains all of the colors. Or, and we'll see this specifically laid out in a little bit, or you can say, here's a color, here's a position, color, position, color, position, color, position in one buffer. That's an interleave buffer. One buffer that has all of the information in it. Right. So buffers are going to be organized into array objects. Right? An array object is going to potentially contain a bunch of buffers that specifies some chunk of geometry that then ultimately the GPU is going to know how to deal with. Right? So we have buffers that are inside of these vertex arrays that we're going to hand to the GPU. It's going to know how to do the right thing. Right? But this is how stuff is passed to it. Right? Vertex buffer objects. They hold data about vertices. Right? You bind a VBO, making it the active one for the operations that you're currently working on, which things like putting the data in there, specifying its format, and so on. So you say, all right, generate a buffer, bind it, now let me tell you about it. Right? This is the one we're working with, let me tell you about it. A vertex array object is the parent to that. Right? The vertex array object holds potentially an array of vertex buffer objects. It's going to have at least one, usually at least two. The proper way, it's going to have two usually. So we start off, we create a vertex array object. We bind it Then we add vertex buffer objects to that. And then later on, anytime we bind that vertex array object again, everything that we bound to that vertex array object is going to come along with it. Right? So we have this hierarchy, vertex array objects and vertex buffer objects. An array has lots of buffers in it. The buffers have all of our attributes of our vertices in it. So, talked about this a little bit already. A vertex can contain a lot of different information. It can have things like position, color, those are obvious ones. Some less than obvious ones, UV coordinates. What UV coordinates are that way that we can relate textures to vertices, right? Say I have a map, my brick wall texture over here that has bricks on it, crude drawing. And I have my triangle over here, and each of those triangles has a vertex. And it would say, okay, this vertex is coming from this point within my texture map. This one comes from this point, and this one comes from this point. So every time it needs to pull something from there, it uses those coordinates. So it's another set of coordinates that map our texture into our triangle, right? So that's that UV. When you hear UV, it's not XY, but it's like XY, but it's a lookup into our texture, right? So that's something you're going to hear a lot about. But for now, position, color, and then normals, which you can recalculate using your winding order and your cross product and things. But there's sometimes you might notice that a vertex can be shared by lots of different triangles. Sometimes it's nice to know, all right, shorthand to say, as far as the overall mesh goes, as far as the global sense of things go, here's the normal for that vertex, so you're not recalculating it every time, right? Eventually, maybe brute force will just do it, but we often use normals to make life a lot easier, right? Now, once we have all those are the things this is how we're going to talk to our shaders, our little programs that we're going to create that really are responsible for doing the interesting stuff, right? Pass everything over to the GPU, and ultimately the shaders are going to be what uses these things. All right, so here's a quick example of not a shader, but of a little bit more when we talked about the interleaved vertex attributes. So after we have a buffer, it might have, say, a couple of different things in here. We'd say the first attribute is the position. The second attribute is this UV, right? So we might have 12 bytes, which are 3 floats. Three floats, an X, Y, and a Z for the position. Then we have 2 floats, a U and a V for that texture coordinate. And then we have for the next one, the next vertex, another 12 bytes, another 8 bytes of UV, and so on and so on and so on. And this GL vertex attribute pointer is what tells it how to kind of parse through there. Now, the good news about all of this is that if you do the Learning OpenGL course of things, if you go through those tutorials to see, okay, how do I get an individual, not a pixel, an individual triangle on the screen, it's also going to lead you through this again. You can jump through and just look at the source code if you want, or just look directly at the Sandbox if you want. But these snippets are kind of arranged in ways that will hopefully make life a little less daunting. But as you're reading, I guess some of this is sort of like designed around not necessarily writing the code from scratch, but if you look at the Sandbox and you see these things, or you look at the example code and you see these things, you'll kind of remember what they are. I don't expect you, it's a good practice to go through your first window, your first dot, and so on. But we want to get going kind of a little quicker than that. Yeah?
So the vertex is just a point, right?
A vertex is
It's just a point, right?
a point in space.
Yeah, so for the color, is that vertex to the next vertex? Or
That depends on what the shader decides to do with it, right? And a vertex isn't really a point. It's not really a point. It contains a position. So yes, it defines a point potentially, but it's not, it's squishy. It's a little bit squishy, and this is where we can get interesting, right? It's designed around the notion of being a point, right? Because we have triangles and so on. As you get into doing crazy things like, you know, GPU programming, or you know, kind of supercomputer. Or if you're like Bitcoin, you're mining Bitcoin on your GPU, you're going to wind up using vertices and things in all sorts of different crazy ways where they're really just collections of attributes. So as a purist, I want to say, well, they're not just points, but from a graphics perspective, I want to say they're just points. So yes. All right. So here's an example of what that would look like. Here's another example. So this might contain a position, a normal, and a UV, right? And so on. And so this would be potentially an interleaved UV, right? So we have, how did that one sneak in there? I don't like that one. Oh yeah, okay, here we go. So we have the position, you know, 3 floats, the normal, another 3 floats, and the color, 3 floats. It will have things you need to know about it, things you need to tell the shader about. Once it has these just data, just these bytes, how does it know these 3 are a position, and these 3 are a normal, and those 2 are a color, or those 3 are a color? How does it know that? Well, you have to specify things like the position offset. So the position starts at the beginning of one of these vertices. The normal is actually here. What is this? It's 3 times the size of a float. So basically, it's going to be 3 times 4, 12 bytes after the other one is where you find the normal. The next one is 6 times 12, or 6 times 4, 6, yes. That many bytes past the beginning of this vertex, right? So you have these offsets that are specified. Let's see. This slide should be before that slide. Here's the rework on these. All right, you'll see in here, size of vertex is this stride that gets you from vertex to vertex. This 0 is the position offset. This 12 is the normal offset. This 24 is the UV offset. Right? So part of what we're specifying here in this vertex attribute pointer, this last bit here tells us where those things are within that structure. And the size of the whole vertex, all these things always tell us, okay, how do we get to the next one in that buffer? The other things that it's telling you about here, okay, 0, 1, 2, those are the IDs of that attribute. Right? So when the shader needs to refer to something, you can tell, okay, use the 0th one. And it knows 0 is using the positions. Use the first one, okay, that's the normals. Use the second one, that's the UVs. Right? So that's how this vertex attribute pointer breaks down so far. Right? Then we tell it how many bits of data, not bits, but how many units of data there are in there. So like in this case, there's 3 floats is the first one. 3 floats, that one. 2 floats is this one. So we have ID, the number of things in there, and then kind of the unit size of each of those things in there. Don't worry about this one. And then we have the way to kind of traverse here, right? So we're telling the hardware how to parse through this data. That's where those numbers are coming from. Right? Stride is the term used to say, okay, to get from row to the next row to the next row to the next row, we move across by the stride. Right? Yeah. All right. Somehow we set up buffers, we made room for array objects, we generated a bunch of buffers that we pushed different attributes into. We told the GPU those where those attributes now live. How do we get the damn GPU to actually do anything with those? How do we kick it off? There are a couple of different ways. I highly recommend, you'll see most of the time we're going to use GL draw elements, is where suddenly we say, okay, now you've got everything you need. Whatever the current vertex array object is, you're free to go and go draw that. Okay. GL draw elements, typically we use that. You can also use, there are a few other GL draw functions, GL draw arrays, but we like to use GL draw elements, because that's what, when we're referring to vertices by their indexes, their indices, we're going to use the draw elements version for that. Right? So normally it says, okay, GL draw elements, if you've given it an index buffer already, it just knows how to just draw it. Otherwise, you can just say, okay, draw elements and pass it a new index buffer, and it'll draw the geometry according to those elements. Another possibility. You do tell it, you sort of inform it sort of the structure of the geometry just a little bit so that it knows, is it a triangle strip? Is it a set of just triangles? Is it something else? Is it quads? Don't do that one. Normally we're talking about triangles and triangle strips. You can do points, right? If you want to make each vertex literally a point in space, you could just say, okay, just draw it like that. Can do it, certainly. Right. So I said we like to use indices, indexes. Where do they come from? Where do they live if not part of the vertex? They're not part of the vertex. They're some way of saying, hey, this vertex, that vertex, and so on. Right? If we have a bunch of different triangles, they may be reusing vertices, so they're kind of distinct. They're a different thing. We don't have one index. Well, we do have an index uniquely defines a particular vertex we're going to draw with, but in a mesh or in an element array that we're going to draw, an index can occur multiple times, right? You could say 0, 1, 2, 1, 3, 1, 5, and so on and so on. So we need some separate structure to store that. That's not technically a vertex attribute, right? Because it's not an attribute of the vertex. It's a means of referring to it. But we actually do use the vertex buffer objects also to store those. Right? So when I was saying usually in our preferred way of drawing, preferred way of working, we have two vertex buffer objects. Usually one that contains the real attributes, and the other one that contains the indices. Right? The indices one is the one that's more likely to change, so we can update that and not worry about what's going on there. So we set up an element array instead of a buffer array, instead of an attribute array, we have an element array to specify the set of indices. So it looks like this, right? You'd be surprised the number of people in game architecture who I say, did you check? Did you set this to element array buffer instead of attribute array buffer? Like, oh, that's what it was. The bane of everyone's existence, right? Just gotta remember about this one, that it's different. Indices are different, just enough to make your life crazy. So an index specifies a vertex to use. It is not an attribute of a vertex. Attributes can be interleaved or in separate VBOs, but the element array buffer needs to be its own VBO, its own vertex buffer object. So be careful when you set those up eventually, or when you're looking at them. That's why you'll see dedicated ones. Now, this is looking a little bit more like a bit of sample code you could actually do something with. All right. So we have in memory somewhere in our CPU now, we have a simple set of vertex positions. We have 3 vertex positions, right, left, right, and top for our 3 positions on our triangle. And we're going to do a bit of setup. We say, okay, generate a vertex array for us. Right? Whenever we want to draw something, a mesh or anything, we need a vertex array object, the top of the hierarchy for it. And then we tell it, okay, how many buffers do you want us to generate? Right here we're doing our generate part. GL gen buffers. We just create one vertex buffer object at this point. This is the brute force way, so we're not going to actually use indices in this one. So we say GL bind vertex array, meaning that's the one we're going to use. We generate it, now we bind it. Now we say, okay, now we're going to want to use this VBO, which we just created up here, bind that. So now we know we're in this hierarchy and we're talking about this particular vertex buffer. We go ahead, we copy our vertices, or we, the number of, let's see, how's this going? Well, when there's copying the whole buffer, this much data starting here, and we're going to later on use that for static drawing. All right, so this is the important part. This is updating, giving the data over to the GPU. Yes?
So the GL array buffer is a keyword for the GPU?
Well, you're only going to be, this is always, you have two types of buffers here. You have the array buffers and element buffers, but this is always what's going over on the GPU, right? So binding buffers, you're never going to have a, be careful when I say that. In normal operation, you're not going to have a vertex buffer object anywhere other than on the GPU. You're never going to have a vertex array object anywhere other than on the, right, from your perspective. What the drivers are doing, it's kind of up to them to say, okay, how are you doing this transfer here? But from our perspective as the CPU program, ideally, it's just going to say, okay, you gave me this buffer, blam, I put it, magically down on the GPU's, in the GPU's memory. There's all sorts of different variations on that one. But normally, these vertex buffer objects, they're a black box as far as we're concerned. They belong to OpenGL. They probably live on the GPU, in all likelihood. Okay. So, we've more or less got everything to the card that it needs at this point to draw that triangle. Our first glimpse at shaders. All right. So back in the day, fixed pipeline, it would just say, all right, I know what to do. You've already described something that's fairly obvious. We have a bunch of indices. Okay, I'm going to, take care of that. I'm going to rasterize those things. I know how to generate the values in between, do the right thing. So these are basically what the fixed pipeline would do, right? Sometimes we're writing shaders that look an awful lot like in our early careers here, are going to look an awful lot like very simple, dumb shaders that would likely be what the fixed function pipeline would have done anyway. So these are actually two shaders here. They'd be, we'll talk about how you load shaders in a bit, but we just want to know what they are at this point. The two main shaders that we mostly talk about, used to be the only shaders that we really program, were vertex shaders and fragment shaders. Right. And basically, when we refer to a pipeline, there's always a pipeline, a bunch of different stages in that pipeline. It has to go, something has to go from, through the different pieces of the pipeline to get to the end, to ultimately have pixels on the screen. So we start off with what we specified, vertexes. Right? That's the first thing. We're feeding our pipeline vertices. I always like to give them equal opportunity. Vertexes, vertices. I should one of these days decide one or the other. That's my ADHD coming out. I'm obsessive compulsive to continuously keep changing. But anyway, so at the pipeline, the beginning of the pipeline, we have vertices. We're kind of pushing them into the pipeline. The first stage, first programmable stage that we're really interested in is this vertex shader. That's a bit of code we can run in there, and they're going to hit that. And it may be that a whole bunch are going to hit simultaneously a bunch of different vertex shaders, right? Now we're in that parallel processing land that the Mythbusters pointed out to us, right? We pass in, somehow we poured in the funnel a whole bunch of vertices, a bunch of paintballs, and they all trickle down into each one of those barrels. Each one of those barrels is going to run that code, right? Because we have tons and tons of them, thousands of them. So the simplest vertex shader, it would say, all right, first there's a bit up there that hash version 330 core, there are ways to say, all right, I require this level of functionality. I wrote this shader making these assumptions about the way that GLSL, the graphics language shader language, GL shader language. So you'll often see this version 330 core, 99% of what we're going to do, no, not 99%, 80% of what we're going to do will only require that much. And the second thing you see there is layout location 0. So way back when we were talking about vertex buffer attributes and using our vertex attribute pointer, remember we said 0, 1, 2, 3, 0 happened to be position. In this case, in our dumb code here, we really only have 1, right? So there really wasn't much to set up there. But we're going to say, okay, in the 0th location is a vector 3 that gives me the 3 position values, x, y, and z. So I can refer to those as a pos, a position. And it's the job of the shader then to do whatever transformation, whatever changes, whatever it wants to do, rotate it, move it, spin it around, give you back something entirely different. Do whatever processing you want in there. And GLSL and HLSL, which is the DirectX version and so on, shader languages have become more and more powerful in terms of what they can do. They can branch, they can loop, they can do all kinds of stuff. GPUs have become way more interesting than they used to be, which is why you can't buy any of them right now because everyone's mining Bitcoin on them. So the simplest, most brain-dead way, if we want to emulate what would be going on in the old days, is we would just pass back that vector, or that vec3, that position, but we would sort of turn into a homogeneous, we would put a 1 at the end and say, okay, it is a point in space. We always want to add a 1 just in case, any sorts of transformations. We're going to talk a little bit about that next time, about homogeneous coordinates and so on. But for now, just assume that we're going to pass it a 1. So we give it back. All right, yep. We kind of put our seal of approval on it. We say, don't do anything, or we haven't done anything. We're just passing this vertex through with the shader. Dumb shader. In fact, in a lot of implementations, you leave that off and you don't load a vertex shader. It'll just be like, got this. I'll do that for you. No problem. Now, this bit here, oh, yeah, what am I saying? This bit here is actually, it is not the fragment shader. Why was I thinking it wasn't? I think the next one is. This is loading the vertex shader. So this is how, this should have been on the CPU side. Sorry, I'm running out of class this morning. I lost my mind. Left that part at home. So the shader programs, how do you program? How do you get them? How do you compile code for them? How do you do that? We know how to, in Visual Studio, we're creating all our code, compiling it, linking it, running it, doing all that kind of stuff. How do you get the shader code onto the GPU? Well, they basically get compiled and linked and loaded, and all that kind of stuff happens at runtime, right? Because you don't know specifically what card it's on. You don't know what capabilities of that card are, and so that sort of thing. So as part of your CPU program, there are ways to say, all right, create a shader, right? It's going to create a vertex shader. Give it source code. So your program may very well have some source code in it. And that source code would look an awful lot like that. Be just text. Just pass that down, tell it, yep, that's some shader source code, compile it. Right, so we're actually going to be building, compiling programs on the fly. Right? Fragment shaders, on the other hand, let's talk about the fragment shader, and we're going to resolve everything down here. The fragment shader's job, fragment shaders are, there's a lot more of them. They do a lot more heavy lifting. Well, maybe not, I don't know if it's heavy lifting or not, but ultimately, when you have a triangle and somehow someone has said, you know what, the point on that triangle is visible in the end. We've culled things, which means we've decided what's facing the back, what's facing the forward, what's not on the screen, and so on and so forth, so forth. It says, okay, this particular piece of this triangle is visible for some reason. We know we need to draw it. This particular spot on the triangle. So here you go. And it's the job of the fragment shader to actually draw the equivalent of that pixel, right? To provide the color, one of the most important things, the color to put ultimately in the frame buffer for that spot. So you may have 3 vertices, but you may have a few pixels, a few fragments, or you may have hundreds of fragments, you may have thousands, you may have millions of fragments that are associated with those 3 vertices. The GPU is handling that for you, right? We'll talk about that a lot more later. It's always, courses I'm always involved in are like very chicken and egg. It's like, okay, we gotta get there first, and then we'll look back and it'll make perfect sense. But for now, we really just have to think, all right, somehow it's magically saying draw this pixel. And it will even give you an interpolated version of its location. It'll give, the GPU is doing all kinds of great stuff. Saying, okay, I've figured out exactly where on the screen that is for you, and you can use that information or not. Or you can just say, give me what color you want me to put there. Right? And so the simplest version of a fragment shader is, here's a color. Please color this fragment. Put that color there. And in this case, so we have vector 4, right, which is think of it as, it's just an array of 4 floats in our case. That's going to be a red value, a green value, a blue value, and potentially an alpha, a transparency value. We'll just leave it at 1 for now. Right. We end at 1235, right? All right. So that's going to say, okay, what color should this pixel be? And we do the compiling of it very similarly how we did the vertex. And a shader program is actually made up of a combination of a vertex shader and a fragment shader. So we create a program, we give it the vertex shader, the fragment shader, we attach those to it, we link it, just like we would link our CPU program, and ultimately, after we tell it to draw the arrays, we tell it, okay, use that program, bind that vertex array object that we talked about. Finally, GL draw arrays, which is the one I told you we weren't going to use all that much. Because this is the one we're just saying, okay, we have 3 points, so therefore we're just going to draw them in that order. It's a simple triangle. It says, okay, draw triangles. There are 3 vertexes, vertices. Just draw it. Boom. There it is. Right? So then whatever color we were specifying in there, we had those vertices, and away it goes. So that certainly seems quite primitive, but it's sort of the fundamental of everything. I'm going to reserve. Yeah, we're going to talk about other stuff. The reason it's quite primitive, and I'll anticipate a question, right? We had no notion of cameras or space or whatever. We just had, like, here's a location. Here's 0, it's 0, 0 to 1, 1 or something like that. Where does that, how big is that? What does it mean? What does it look like? How's it presented? What's perspective? What's rotations? Where are the transformations coming in? There's tons and tons and tons of other things that we'll reserve for the moment. And let's see if I can actually, so here is, oh, no, there. Now you should go back to mirroring everything, I guess. See if I can. All right. Keep those settings. So, believe it or not, our simple Sandbox version, if you wind up using, let's see, I'll do the quick default. So in the Sandbox, we have a data folder, just so you know about the data folder. And data folder, there's two images, which we're going to use for textures. And there's also a texture.vs and a fragment.vs, which are going to be some potential shader source code that we may wind up using. But the real important stuff lives in project 1, and there's going to be two different CPP files. When it first installs, it puts an underscore after the main one so that CMake doesn't automatically bind it into the project. But we'll go ahead, and so there'll be a main.cpp, which has an underscore, and a simple.cpp, which is the one it's going to wind up kind of baking in for the first time you run it. So let's give it that way. So I'm going to remove, and I will add back in existing item simple.cpp. And I've probably already broken this code to be a little bit different than the version that you're used to, if you've already downloaded the Sandbox. All right. So it does draw a triangle. Yay, it still draws a triangle. And it will follow, this actually is written with the Learning OpenGL website and that book in mind, so it'll follow that closely. It uses GLAD as the means to kind of provide all the OpenGL functions, but uses GLFW for the keys and so on. And the first time it goes through, it actually, let me see here. No, I kind of messed through it. Okay. I'm going to tell it not to do that. I'm going to tell it not to even use any shaders. Okay, don't use any shaders. And we pass it. This is the default state, right? Doesn't use any shaders. It just says, all right, here's 3 points, and it even does it in the immediate mode way. Right. So it uses this here. A GL begin sets 3 vertices and ends and draws the triangle that way. So OpenGL, all these things, they love to quote unquote deprecate functionality, which means like, yeah, don't use that, but it'll stick around just in case you do. So even these days, you can still, unless you specify, I think 4.0, in which case I think it did wipe this out at some point. But this is the old way of doing triangles. Just say, okay, begin triangle, here are the points of the triangle, draw it. It's not even using the shaders. Right. Then, let me do something slightly crazy. And this is to encourage you to kind of play around with some of the code in here. Your version, I think we'll have this version in there. We'll say, okay, I'm going to go ahead and use our shaders. And reload. And now we have a red triangle that's half the size. So we use the same vertices, but this vertex shader that I just told it to use does, I commented out some code. You'll notice it follows very C-like in syntax there. There's my little shader up there. So my simplified version, all I did now is I changed GL position. Instead of just putting in the positions I'm handed, there we go, I divided all of them in half. So everything became small. I scaled them all down. Right? So this is something that the vertex shader can do. It operates on all of the different vertices, scales them down, for example. And then I have my fragment shader, which I should say fragment. Sorry if you're referring to the code and you find that one. Where the fragment shader in this case is now saying, well, all right, every pixel that you give to me to draw within that triangle, I'm going to use this color, which is full red, 0 green, 0 blue, fully opaque. So instead of that white triangle, I get a red triangle. All right, so that's the sort of thing we can do. We specify the look of a particular fragment and then any manipulation of the geometry through, the vertex shader manipulates our geometry. The fragment shader manipulates how we ultimately draw those pixels. All right. There are games you can play, and if you're looking in here and you're wondering, like, what's this other part of the vertex shader that you put here? There's nothing saying that, again, when you're mining Bitcoin or you're doing whatever you want, you can really go crazy inside of these shaders and say, okay, I'm going to ignore the vertices you sent me. I know you sent me 3 vertices, but that's all I'm interested in, that there are 3 of them. And this weird shader here, if we uncomment that code out and run it, right, we run this. We get a very different triangle. It's still a red triangle, but the geometry is all different. Right? It's not just a scaled version of it. It's different vertices. And we did that by actually ignoring the position that we were passed and playing some games to say, well, okay, I know if you passed me 3 vertices, every time you pass me 3, the first one is going to be at this location, the second one's going to be at this location, the third one's going to be at that location. So you can entirely override things, do all sorts of crazy, interesting things. All right. So does everyone, more or less everyone, except we're figuring out the Mac at this point, does everyone else have this running to some degree on theirs? Okay. It's going to be important to do that, because what I'm going to want to do is I'm going to refer to this, and I'm going to want you to be able to, it's going to be like sort of our lab to kind of mess around with. Where it gets particularly interesting is eventually we'll say, okay, we're going to stop using the simple version, and we're going to add the normal main CPP. All right. This version is going to have, for example, here's our stuff we're going to load into our vertex buffer. Our positions, our colors, our texture coordinates. Here's our set of indices. Right, here's everything being set up. And we'll be able to modify it, experiment with it, and more excitingly, I think it's the exciting part, to kind of make things interactive. Right, so I spent a bunch of time on this, so I'm hoping that you'll find it interesting, useful, is that we can actually go in and change our code here. Like our shader, because we had that compile, load, link, etc., etc. I can change what the shader is doing. I can give it new code, compile it, link it, go to do the thing. So we can really kind of see what the effect of certain transformations are, how we pass it uniforms, how we do all those things interactively. So it's going to be important that you get this up and running as quickly as possible, right? So this is sort of the footnote to the homework. This is the homework, which is the simple version, the questions about, the last lecture and a little bit history and so on. No new things based on what we had today. But the other footnote of the homework for next time is basically to make sure you have the Sandbox code running. You should at least be seeing simple triangle. If you want to start breaking it, doing different things with it, see what it does. You should be able to compare it very much with the OpenGL, learning OpenGL. So if you want to move ahead and start, referring to that, comparing the two, familiarizing yourself with that, that'll be good, right? So I'm not going to sort of explicitly, in reading through a lot of other people's syllabi and so on, so it's like, okay, how much time do I expect everyone to spend in the course? And like okay. The homeworks are going to be pretty straightforward, and a lot of time, it may seem like, project-wise and so on, you could, you're probably not going to spend 20 hours of your other time worrying about this class. But I am basically hoping that what you're going to be doing is following through a lot of the tutorials. I'm not going to collect the results of those. If it's learning OpenGL or OGL.dev or something like that, you should find one of those sites and be prepared, because I'm going to try to push things at that same pace. But if you have issues and so on, it's going to sink in a lot better by you really trying out the stuff. That's interesting. So you should be, even with the simple homework stuff, if I haven't assigned anything, you got it up and running. That's great. But what will really be important is what you do then. And I'm sort of expecting that you're going to be looking at the learning OpenGL stuff. It's reading the chapter of the book, basically. The first one. Learn OpenGL. Right. The general response I got from people was that they were happy to not spend another $50 on a textbook, and they can just go ahead and use this, which is fine because it's great. It is a really good site. But based on today, these first parts, OpenGL, creating a window, hello triangle, and shaders, that's basically what we covered today, right? So if you have any questions, you want to make sure you know how to do it, you should be able to have the sandbox running and kind of work your way through that, right? What I demonstrate in the sandbox right now is definitely covered by those tutorials as well. Next time we'll be getting into more on the transformations specifically. And for that, we're going to want to be plugging things into, and I'm going to give you some new add-ons to the sandbox that allow you to dynamically and interactively work with transformations, some of the math functions and things. So that's it. It's 12:35. First day in person. Was it terrible? I'm going to have like such a mark on my forehead from this thing here. I 3D printed these myself. Oh, the perfect forehead for it. I should have a Is everybody on Discord still good, or? Okay. We'll see you, maybe we'll see you in person next week? Oh, and next week, I guess, Memorial Day is Monday, so we're not meeting Monday, but I think we wind up meeting on which? Wednesday, yeah. So, there we go. Really? Oh, I didn't switch the, okay, yes. Okay, yeah, it's tricky here because in terms of the number of monitors, I have to juggle here. All right, we'll see what we can do. So you're going to be remote for the whole semester? Okay, all right. As long as I know that, that's good. Okay, I mean not good, but we'll deal with it. All right. Yep. No, I'm very familiar with that. Okay, we'll quote unquote see you next week. All right, bye. And I have to stop this before it fills.